So I'll be talking about nonlinear transport and how it is related to quantum geometry and crystalline symmetries of systems. The material aspect is there, but I will not focus on some particular material. So the main message that I want to convey is that when you go to the higher order transport, there are several contributions that appear. It's like a zoo. And what we found, we basically identified some new animals to this zoo, and they are interesting. Okay. All right. So let's start with the question that what is nonlinear transport? We are all familiar with linear transport in a conductor, which is given by a linear IV characteristic where voltage is linearly proportional to the current. And we can model such transport by using Ohm's law. When the IV characteristic deviates from such a linear relationship, we call it nonlinear transport. And in the small bias regime, we can model this kind of transport using these equations. Now, perturbation theory teaches us that if you make the bias stronger and stronger, there is no surprise that some nonlinear response will always appear in a system, right? So the question is that when and why the nonlinear transport is important. The first scenario where the nonlinear transport can be important is when the lower order responses vanishes. To see this, let's take the example of anomalous Hall effect. And let's say we want to see the anomalous Hall effect in a system where there is time reversal symmetry. Now, symmetry argument says that you will get 0 anomalous Hall response in this system. Not only that, let's say now you consider a system where both the time reversal and the inversion symmetry is broken, but the combined symmetry is preserved. For example, you take CUMNS. In such systems also, the linear anomalous Hall effect will also vanish. So in such scenario, where this lower order responses vanishes, the higher order response can be interesting and worth to explore. There is one more reason you can go to the higher order response is when the response reveals something non-trivial about the system. To understand this, let's again go back to the example of anomalous Hall effect, and this time let's consider a ferromagnetic system which usually shows anomalous Hall effect. Now we know that there are 3 mechanisms behind this anomalous Hall effect. The first two, namely the side jump and skew scattering, are extrinsic in nature. However, there is one more which comes from intrinsic deflection of the carriers. Now this third mechanism has played a very important role in condensed matter physics. There are several reasons behind that. The first one is that it is intrinsic in nature, that it does not depend on scattering time. And the second one, that it originates from something called Bailey curvature. I guess you have all heard about it. It's one of the quantum geometric quantities which is completely determined by the wave function of the system. Due to these two nature, that it's intrinsic in nature and it depends only on the quantum geometry, in certain scenario this effect can be quantized. For example, in quantum anomalous Hall effect, you will get some quantized response. So the point that I'm trying to make is that if in your higher order response you get such kind of scenario where your response is like intrinsic and depends on some quantum geometry, then I guess it is important to explore them. So with this motivation, in the rest of my talk, I will discuss about quantum geometry since it appears in kind of all the higher order responses. And then I will go to our work on second order and third order transport. So what is quantum geometry? So when we think about geometry, the first thing that comes to our mind is distance between 2 points, okay? And the concepts of quantum geometry appear very naturally if you define the distance between 2 quantum states. So here is a caution that this distance is not the distance in the reciprocal space, okay? It's a distance in the Hilbert space. So to understand that, let's take this example of spin half system in the Bloch sphere. So if I consider 2 states, one in the north pole, the other is on the south pole, then they are orthogonal and the distance is maximum. If I consider 2 states which resides on the same pole, then the distance is minimum and it's like parallel. We can express this distance in terms of a quantity q and ij, which is called quantum geometric tensor. How this is relevant? So the imaginary part of this quantity is the Berry curvature that I talked about, and the imaginary part, the real part is something called quantum metric. We all know about this Berry curvature, however, this quantum metric is a bit new. So let's try to understand what is this quantity, particularly in the context of crystals. To understand that, let's take an example of 1D lattice with 2 orbitals. In that case, the system will have 2 bands. And now let's consider a system where there is no orbital mixing. So the orbital nature of the conduction band is very different from the orbital nature of the valence band. And you want to calculate the distance between the states k and k plus dk. Since you are looking at a particular pole of this Bloch sphere, you will find that the distance will be 0, and such case we call trivial geometry. Okay? But if you consider a system where there is orbital mixing in the system, then the distance between k and k plus dk will not be 0, and the system will have some non-trivial geometry. So basically we are looking somewhere in the middle. Now this quantum metric is actually very shy. It hardly appears any linear transport coefficient, and it acts as a motivation to go beyond the linear and explore the nonlinear responses. But you may ask the question that, okay, I have defined quantum geometry, but why do we even expect that quantum geometry will appear in transport? So I'll give you 2 reasons. The first one is a bit of mathematical construction. So when we consider this interaction Hamiltonian between the electric field and the charge carriers, then we define this Hamiltonian where r is the position operator. Now this position operator in the Bloch basis gives us the fundamental building block of quantum geometry, the Berry connection. And the quantities that I define, Berry curvature and quantum metric, are nothing but some combination of this Berry connection. So when we calculate transport, we are basically calculating velocity, position, acceleration, and all the band geometric quantities appear through this position operator, the Berry connection. There is one more intuitive way to see this. For that, let's consider a non-trivial system, and when you apply electric field in the system, what happens that the carrier moves from a point k to k plus dk. This kind of motion in the reciprocal space, you can think this kind of motion in the real space, that there is an interorbital motion in the system, and this kind of interorbital motion appears through the quantum geometry. Okay, so now I will move to second order transport, but before that, let's just first recap the first order transport just to build some intuition. Okay. So in first order transport, we have 2 kinds of contribution. One comes from the group velocity and the shift of the Fermi surface. This one is extrinsic, that it depends on the scattering time, and it is dissipative in nature, so j dot E not equals to 0. We call it Drude contribution. And there is one more contribution which comes from the anomalous velocity, and this is intrinsic in nature, does not depend on scattering time, and it is dissipation-less. Okay. Based on this criteria, if we want to categorize these 2 responses, then we can make a table like this. I want to emphasize here that since the anomalous Hall effect always requires time reversal symmetry breaking, that's why it appears in the tau odd column. Okay. Okay, so based on the question that I introduced in my initial slides, that in a time reversal symmetric system, the linear anomalous Hall effect vanishes. Back in 2015, Professor Weizmann and Liangfu proposed a nonlinear Hall effect characterized by this kind of quadratic IV characteristic. Okay, and they say that this kind of Hall effect can originate from the combination of anomalous velocity E cross omega and a first order shift in the Fermi surface. Note that the 2 electric field, one appears from the velocity and the other appears from the distribution function. If we write this second order Hall effect, we can write it in terms of the derivative of the Berry curvature, hence it is called Berry curvature dipole. Since this is a second order response, so to see this effect, you always have to break inversion symmetry. And since the proposal, there has been several experimental reports, including this on bilayer WTE2. Based on the other question that in a PT symmetric system, the linear anomalous Hall effect vanishes, back in 2014, Professor Xian and company proposed another Hall effect, again characterized by this quadratic IB characteristic. But this time they said that this Hall effect originates a second order correction to the anomalous velocity. Okay? There is no shift in the Fermi surface. Due to the, so both the electric field actually appears from the velocity. Now this effect is interesting because first of all it is intrinsic in nature, it does not depend on scattering time. And the other point is that unlike the other Hall effects that I mentioned, like anomalous Hall effect or Berry curvature dipole, all appeared from this Berry curvature, but this one originated from the quantum metric, the other quantum geometric quantity. This effect has been also seen in experiment in MnBi2Te4 with black phosphorus just last year. Okay. Now when we started working on this field, the thing we noted is that it's like all the time the band geometric or the quantum geometric quantities arise in the dissipationless Hall responses. For example, you see anomalous Hall effect, that's a Hall response. When we come to second order response, then both the Berry curvature dipole and this quantum metric dipole is Hall in nature. If you calculate the dissipative part, then it will be only given by this trivial nonlinear Drude contribution. So we asked the question that can the quantum geometry also induce some dissipative response in a system? And I'm happy to share that we found a contribution where we see quantum metric leads to some dissipative response. How do we find that? We constructed a density matrix formalism. Here rho n is the density matrix, H naught is the unperturbed Hamiltonian, Hi is the interaction Hamiltonian, and rho naught is the equilibrium density matrix, which is basically given by the occupation of the two bands. If I apply electric field in the system, there will be some correction in the diagonal part and some off diagonal part will also arise. Combined with the velocity operator, this will give rise to this new contribution. Okay? There is a very intuitive semi-classical picture to see this new effect. This actually appears from the second order correction to the energy. So this will give rise to a new velocity which is second order in electric field, and this will lead to this effect. Why this response is special? So first of all, it's a dissipative response where the quantum geometry appears. It independent of scattering time and it depends on the quantum metric. There are some features. One, if you want to see this response, you have to break both the time reversal and the inversion symmetry. And this responses peaks near the band edge that we find in a simple gapped tilted Dirac model. Then we calculated this coefficient for a PT symmetric system, and we find finite responses in this model also. So now the question can be that is this effect measurable? Well, we find two experimental reports, one from Professor Weibo Gao's group and the other from Professor Shu Yang-Zhu's group, who both have basically reported this kind of intrinsic dissipative conductivity which depends, which comes from quantum geometry. Okay, now I will go to the third order transport. So when we finished this work on second order transport, we thought that okay, can we extend this to higher order? And if so, then what are the interesting scenarios where this effect can play a very vital role? Okay, here again symmetry comes into the picture. Now let's consider a system where you have both the time reversal and the inversion symmetry. For example, you consider graphene. You will see that the time reversal symmetry will kill the linear Hall effect and the inversion symmetry will kill the second order, any second order response. If you consider a system where the time reversal is broken, but both the inversion and PT symmetry is present, for example, if you consider bulk CR SBR, you will find that the PT symmetry will kill the linear anomalous Hall effect, and again inversion symmetry will kill the second order responses. So in such cases, if you calculate the responses, there are several contributions. I warned you that it's like a zoo, but let's try to understand this zoo. So one of the contribution which we call third order nonlinear Drude comes from the third order shift of the Fermi surface. The other one comes from second order shift of the Fermi surface combined with this anomalous velocity. Sophia discussed about this yesterday. If I combine the second order correction to the energy with the first order shift of the Fermi surface, then I will get a dissipative response. If I combine that with the anomalous velocity, I will get a Hall response. And if you consider the third order correction in the anomalous velocity, you will get an intrinsic Hall effect. So these effects were known before our work. What we find, we basically identify two new contributions. One comes from this energy correction, third order energy correction. It appears in the dissipative responses. And one more comes from a correction to the Berry curvature. So now you may think that, okay, in third order there are so many contributions. How do you even know that when we do experiment, we are measuring what response? So for that, there is some scaling laws which can help us. All you have to do is like you measure any higher order response. This response you plot with sigma xx, the usual conductivity, and you find out the coefficient of sigma x square or sigma xx, and this coefficient will tell you that the conductivity which you are seeing depends on which power of scattering time. So using this scattering time analysis, you can most probably figure out that which response you are seeing in your experiment. Then we did a model calculation for this. This is how the dispersion looks, and this is what we get. So here you will, so the left one is the ohmic contribution, the dissipative contribution, and the second one is the Hall contribution. You will see three curves here. The black is total, the blue one what was known, and the red one what we predicted. And we find that the red one contributes significantly. And finally, what we did, we basically analyzed all the 122 magnetic point groups and figured out that which of the point groups will be good for what kind of response. So you will get all the information in this table. Okay, so now I'm kind of end of my talk. So the takeaway you can have from this talk is that the symmetry and quantum geometry plays very important role when you go to the higher order responses. And I kind of try to give a complete picture of all the responses, first order, second order, and third order. And this highlighted contributions what we predicted. Okay, finally I will acknowledge all the people with whom I worked from IIT Kanpur, India, where I did my PhD, Professor Dimi Kalsar from UNSW, and Professor Binghai Yan, with whom I am working in Weizmann. And thanks to all of you for your attention.